Hello, my name is Guilherme and I am a student at the Federal University of Ouro Preto, and I will present to you my work about employment of generative adversarial networks to train an SSVEP-based BCI. Brain-computer interface systems allows communication through the interpretation of brain signals. However, to use these systems, it is necessary to perform the training stage, which, depending on the user, can take a long time. A paradigm often employed to develop a BCI is the steady-state visual evoked potential, SSVEP, which relates each command of an application with a specific visual stimulus that flickers at a well-defined frequency. So, the objective of this work is to employ a generative adversarial network that generates synthetic EEG SSVEP signals to train a BCI SSVEP system. Our materials and methods are the following. The dataset used for gain training consists of 16 EEG acquisitions of 12 seconds for two visual stimulations flickering at 10 and 12 Hz. Just the signal from the electrode placed at OZ was used, and the signals have been windowed to 2 seconds. The generative adversarial network developed for this task has the following specifications: 400 epochs for training. The generator is composed of 6 dense layers and the discriminator of 7 dense layers. And the output of the generative adversarial network is a synthetic EEG SSVEP signal with 512 examples. For validation, an SSVEP-based BCI was designed using the magnitude of the FFT at 10 and 12 Hz as features and a linear classifier based on least squares. And 2 scenarios were simulated. Scenario 1 with 100% of real EEG SSVEP signals to train the BCI. Scenario 2 with 30% of synthetic data and 17% of real EEG SSVEP data. Figures 1 and 2 shows the FFT of real and synthetic EEG SSVEP signals. In both cases, a major intensity at 10 Hz is noted, although the synthetic signals present a lower signal-to-noise ratio. Also, normalizations during gain training generate a difference in the order of magnitude of the FFT. Considering 20 crossfold validation, the average performances for BCI were 84.5% in Scenario 1 and 88.5% in Scenario 2. So, in conclusion, we have that techniques to simplify the training step of a BCI are important to make these systems feasible for disabled users. The application of GANs to train SSVEP-based BCI is a promising approach for this purpose. The EEG SSVEP signals generated by the GAN in this study proved to be useful in the training process of an SSVEP-based BCI system. And more tests with GANs and the use of preprocessing techniques in the synthetic signals could improve the results. Here we have our references. These are our contacts, and thank you very much.